Okay, welcome back everyone. In this video, we're going to be looking at the range and maximum height of a projectile, as well as the optimal launch angle. So we're going to be doing a little bit of derivations this time, and we're still looking at how we can describe this curved path, and now we're just looking at some properties of this path. We're going to start by actually combining our x and y of t equations. And we want to show that this is the physical path of a projectile. So what you might have noticed is that previously we had an equation for delta x as a function of time, and we had an equation for delta y as a function of time. So now what we're going to do is try to put these together. So delta x as a function of time is equal to vx naught times t. And we're going to assume that x naught equals 0 so that this just turns into x. Likewise, we're going to assume that y naught is 0, so delta y is going to be vy naught times t plus 1/2 gt squared. Okay. And we're going to say, actually for the sake of argument, that in this example, g is positive 9.8. So we need to put a negative sign here for this. Okay, so my strategy is going to be, I'm going to solve this for t, okay? And t is going to be equal to x over vx naught. And I'm going to plug that into my equation for delta y wherever I see t. So delta y is equal to vy naught, vy naught times t, which is x over vx naught. I'll write it like that for fun. And then we have 1 over 1/2 g, and then we have x over vx naught quantity squared. Okay, so we have a little bit of simplifying to do. And the first thing to notice is that vy naught over vx naught is going to be v naught sine theta over v naught cosine theta. So those are going to cancel, and that's where I get my tangent from. So put that in a second. And then we're going to have 1/2 g x squared over, and vx naught squared is going to be v naught cosine theta, and those will get squared. Okay, so if I just kind of rearrange these terms, we have delta y is equal to tangent theta times x minus g over 2 v naught squared cosine squared x, and that's all times x squared. So that's how we show the physical path of a projectile. Now, let's derive the range equation, and we'll also do maximum height because that's pretty easy. So the range equation is for a projectile fired over level ground. So it's very important to make a note of this, that delta y is equal to 0. And if that's not the case, then this range equation is not going to work for you. Okay? And basically range is the same thing as delta x. So we start with that delta x is equal to vx naught times t, and delta y is equal to vy naught t plus 1/2 gt squared. And just like the last one, we're going to say for fun that g is 9.8. So this is actually going to become a negative here. Okay? So now, instead of plugging x into y, we're going to go the opposite way and plug y into x, using the fact that delta y is 0. So this is going to be v naught sine theta times t, and this is going to be minus 1/2 g t squared. Okay? So we have two options for our time here. T could be equal to 0, or cross out one of those, and we could have t is equal to v naught sine theta over g times 2. So that's the one that we want to use, and we're going to take that and plug that in for this time here. So we get delta x is Vx naught, but that's really V naught cosine theta. And then t is going to be 2 V naught sine theta over g. So that's going to simplify a bit into 2 V naught squared sine theta cosine theta over g, which is what we want. Okay, so that's our equation for range. Now the last thing I'm going to do before moving to the next slide is I'm going to find maximum height, and this is actually pretty easy. We don't need to go into depth on this. Maximum height is going to be when Vy is equal to 0. And if we use our forgotten equation, you might remember that V final squared equals V initial squared plus 2a delta y. Okay, so Vy final is going to go to 0. Vy initial is actually V initial sine theta quantity squared. So if I solve that for delta y, I will get delta y is equal to V naught squared sine squared theta over 2g. And that is the maximum height, but I should add in that I want to add any initial height to that. Okay, so the max height equation that I've derived here works pretty much for any situation, but max range is only for when delta y equals 0. Okay, so now the last thing we want to do is we want to show that the maximum range is obtained for a firing angle of 45 degrees. So the first thing that we need to do is to rewrite this using the fact that 2 sine theta cosine theta is the same thing as the sine of 2 theta. So that's just a trig identity that we're going to use. Okay? Then, when do we get our maximum range? Well, the range is going to, max out when our derivative is 0. So when dr d theta is 0. Okay? So what we're going to do is we're going to vary the angle and look at its effect on the range. Okay? So we want the derivative with respect to angle of V naught squared sine of 2 theta all over g. Okay, so the V naught squared over g is a constant that can come out, and then we want the derivative of the sine of 2 theta. So we're going to have the cosine of 2 theta, and then chain rule will be multiplied by 2. Okay, now we want all of that to max out, so we want dr d theta to be equal to 0, which means that 2 V naught squared over g cosine 2 theta equals 0. Basically that constant goes away. Okay, and we're trying to solve the cosine of 2 theta equals 0. Take the inverse cosine of each side, and 2 theta is actually going to be equal to 90 degrees. Right? That's going to give us a cosine of 0. This means that theta is 45 degrees. Okay? And so if you think about this, if we take 45 degrees and plug it back into our angle here, 2 times that is 90. The sine of 90 is 1. So we're going to maximize this function when the sine of 2 theta is equal to 1. Okay? Now it's very important to note that all this is being done without any regard for air resistance, which we're not going to get to until next unit. Okay, so those are some details about projectiles. Next time we're going to move on and talk a little bit about uniform circular motion.